Hello everyone, here is Khaled Omar, and in this video I'm going to demonstrate part 2 of the quality of service videos, and in this video I'm going to demonstrate congestion management and avoidance. So the contents of this video will be only congestion management and avoidance, and we will not demonstrate all the tools, but we will focus only about 2 tools. So first of all, Cisco iOS queuing tools. There are several tools, about 8 tools, and the first one is called class-based weighted fair queuing, and we will demonstrate this tool in this video. The second tool called low latency queuing, LLQ. The third tool is weighted random early detection, or WRED. The fourth tool is modified deficit round robin. The fifth tool is random early detection, or RED. The sixth tool, weighted round robin. The seventh tool, called shaped round robin. And the eighth tool, called resource reservation protocol, or RSVP. Actually, we will make different videos, and each video will take a couple or three queuing tools from these tools. But in this video, I'm going to demonstrate the highlighted with green tools. The first one is class-based weighted fair queuing, and the second one is low latency queuing. So let's start. First of all, let's define what is congestion management. Let me bring the highlighter here first, or the pen. So what is congestion management as a definition? Actually, usually we call it queuing. So when you find the word queuing, it means congestion management. So what congestion management is? It refers to how a router or switch manages packets or frames while they wait to exit a device. When a router receives some packets and these packets wait to exit an interface, the term queuing comes to place. It means that we have to arrange the incoming packets that will exit specific interfaces. So with routers, the waiting occurs when IP forwarding has been completed. It means that the router decided that this specific packet will get out of this interface, this specific interface. So the queuing is always considered to be output queuing with routers. What this means? It means if we have a router here, and this router received packets from this interface, and after it makes the forwarding decision that this specific packet should exit this specific interface, then queuing comes to place. And queuing is considered to be output queuing. So when we have a queue here for this interface, and we will define the types of queues in another slide, we will find out that the router have only output queuing. So with respect to LAN switches often support both output queuing and input queuing, where input queuing is used for received frames that are waiting to be switched to the switch's output interface. What this means? Routers uses only output queuing, but LAN switches supports both output queuing and input queuing. So another term that should be defined here is called congestion avoidance. What is congestion avoidance? It refers to the logic used when deciding if and when packets should be dropped, as a queuing system becomes more congested. If this is the queue, like a cup, and we have packets here, packets, that makes congestion here full. So we have to drop some packets. What determines which packet should be dropped is the congestion avoidance logic. And we will demonstrate later what are the tools and how to drop some packets based on this logic. And which packet exactly should be dropped in case of congestion. So we will start by Cisco routers queuing concepts. And later on we will define and demonstrate LAN switches in another video. So Cisco routers can be configured to perform fancy queuing for packets that are waiting to exit an interface. Let's give an example here. We have a router here. Let's call it R1. This R1 has two interfaces. This interface that is connected to the Ethernet LAN, and this serial interface sorry, that is connected to the WAN. So the bandwidth of the Ethernet interface, the fast Ethernet interface, is 100 megabit per second. And let's assume that we received 5 megabit per second of packets, incoming packets. All these packets are decided by the router to exit this serial 1/1 interface. So the router, the serial interface has bandwidth 1.544 megabit per second, a T1 link, serial link. So if a router receives 5 megabit of traffic every second for the next several seconds, you will have a lot of packets, and the bandwidth of the serial interface is very low. So the end result is that the router will forward some packets and discard other packets. This is not a good solution because many packets will be dropped. So what the router will do? The router places the packets into one or more software queues, which can be managed, thus impacting which packets get to leave next and which packets might be discarded. So here comes to mind the software queues. The router will have different queues that is associated with each interface. So these software queues can manage the incoming packets that is decided to exit a specific interface. And it can determine also which packet of those can be discarded. But in this scenario, no packets are discarded. All the packets are stored inside software queues, and then, as you can see, the order of the packets are different. The blue, green, red became red, green, blue. This is because of the quality of service configured, the queuing. The red packets exited first, the green second, the blue third, even if the blue packets came first. So let's discuss the software queues and the hardware queues. The queues created on an interface by the popularly known queuing tool are called software queues. So what creates software queues? The queuing tool. as these queues are implemented in software. However, when the queuing scheduler picks the next packet to take from the software queues, the packet does not move directly out the interface. So where it goes, the router moves the packet from the interface software queue to a small hardware first in first out queue on each interface. What this means? It means that each router interface has two types of queues: software queues and hardware queue. The hardware queue uses the logic first in first out. There are no queuing on the hardware queue, but the software queues manages the packet by the queuing tool and gave a specific quality of service for these packets. So for the hardware queues, Cisco calls this separate or final queue either the transmit queue or TX or transmit ring or TX ring. Sorry, I think that's something wrong with my throat. So depending on the model of the router, and these queues are called hardware queues. So hardware queues provide the following features. When an interface finishes sending a packet, the next packet from the hardware queue can be encoded and sent out the interface without requiring a software interrupt to the CPU, which ensures full use of interface bandwidth. The second feature is that the hardware queue always use first in first out logic. This makes the decision faster. The third feature, it cannot be affected by iOS queuing tools. That's as mentioned in the previous slide. The hardware queue is not affected by any queuing tools, only the software queues. The fourth feature is that iOS automatically shrinks the length of the hardware queue to a smaller length than the default when a queuing tool is present. The fifth feature is that short hardware queue lengths mean packets are more likely to be in the controllable software queues, giving the software queuing more control of the traffic leaving the interface. So the only function of a hardware queue that can be manipulated is the queue length. And to define this queue length, it is the number of packets in a single queue. How to know the queue length of a specific serial interface? You can use this command. Show controllers, serial, and the interface. Let's assume it is 2/0. Down there you can find the queue length, these two. And the smallest recommended value is 2. And if you want to change this value, you can use the following command. The following interface subcommand. Router config if TX ring limit, we decreased it to 1, which is not recommended. But for example, and here you can see it is changed to 1. So iOS queuing tools can create and manage software queues associated with a physical interface, and then the packets drain into the hardware queue associated with the interface. Simply, the packets first goes to a software queue that is associated with a physical interface. Once the queuing tools do its job, the packets drain into the hardware queue that is associated with the same interface. Additionally, queuing tools can be used in conjunction with traffic shaping. So you can use queuing plus traffic shaping. And to define traffic shaping, it is to delay packets to ensure that a class of packets does not exceed a defined traffic rate. If, for example, you have a link with 5 megabit per second and you choose a specific traffic to use only 1 mega, you can use the traffic shaping tool to delay these packets to not exceed this 1 mega threshold. So while delaying the packets, the shaping function queues the packets by default in a first in first out queue. So depending on the type of shaping tool in use, various queuing tools can be configured to manage the packets delayed by the shaping tool. And for your information, we will have another video that demonstrate traffic shaping and policing, but we will not focus in this video about traffic shaping. Just for your information, the definition about shaping. What is traffic shaping? To delay the packets, to ensure that they are not exceeding a defined traffic rate. And for your information, queuing tools can be used in conjunction with traffic shaping. So let's compare the queuing tools. Cisco IOS provides a wide variety of queuing tools, as you saw in the first slide. There are many queuing tools. The following table summarizes the main characteristics of different queuing tools that you will want to keep in mind while comparing each queuing tool. Let's, for example, take the feature of classification. As a definition, it is the ability to look at the packet headers to choose the right queue for each packet. If you configure different queues, you have to classify which packets should enter each of these queue to apply specific quality of service, to apply specific queuing feature, like giving a specific bandwidth for the first tool that we used, class-based weighted fair queuing, and so on. The second feature is the drop policy. As a definition, the rules used to choose which packets to drop as queues begin to fill. The third feature is scheduling. The logic used to determine which packets should be dequeued next. And then the maximum number of queues. It depends on the model of the router and the memory. And as a definition, it is the number of unique classes of packets for a queuing tool. And by the way, you can use the term queues or classes. So the maximum number of queues is the number of unique classes of packets for a queuing tool. The last one, the last feature, the maximum queue length. It is the maximum number of packets in a single queue. So after we define the number of queues, the maximum number of queues, we have the queue length that define the maximum number of packets inside a single queue. So as we mentioned in the beginning, we will demonstrate only two tools, the class-based weighted fair queuing and the low latency queuing. What each tool does, a class-based weighted fair queuing reserves bandwidths for each queue. What the low latency queue does, it adds to the class-based weighted fair queuing the concept of a priority queue. And we will know later what is priority queue. Both tools use modular quality of service command line interface for configuration, which means that they have robust classification options including access control lists and network-based application recognition. So both tools use almost identical configuration. What is the difference? The one major difference is whether the bandwidth command for class-based weighted fair queuing or the priority command for low latency queuing is used to configure the tool. The configuration is very simple, by the way, as you will see later. And to differentiate between the two tools, the class-based weighted fair queuing uses the bandwidth command, and the low latency queuing uses the priority command. Because both tools use modular quality of service command line interface, both use class maps for classification and policy maps to create a set of classes or queues to be used on an interface. We can use, instead of classes here, queues. The class defined in the policy map each define a single queue. As a result, the term queue and class are often used interchangeably when working with class-based weighted fair queuing and low latency queuing. Both tools support 64 queues, up to 64 queues or classes. So you can configure up to 64 queues or classes for both tools. But the maximum queue length can be changed with the maximum possible value and the default length varying based on the model of the router and the amount of memory installed. So the number of packets inside each queue can be changed based on the model of the router and the amount of memory installed. Both tools also have one special queue called the class default queue. And I think it is not new for you because we defined the class default queue in part 1 of the quality of service videos. The class default, the queue exists even if it is not configured. This queue exists even if it is not configured. So what it does, if a packet does not match any of the explicitly configured classes in a policy map, iOS places the packet into the class default class or queue. So any packet that doesn't match any of the configured classes in a policy map, iOS immediately places the packet inside the class default queue. So the class-based weighted fair queuing settings can be configured for the class default queue. You can, or you can leave it. It's up to you. You can configure class-based weighted fair queuing for the default class or the class default queue. So let's start by the class-based weighted fair queuing, basic features and configuration. And later on we will discuss the low latency queuing. So the class-based weighted fair queuing scheduler guarantees a minimum percentage of a link's bandwidth to each queue. What this means? It means if we have a router here and a serial link and we have different queues here, The class-based weighted fair queuing can reserve and guarantees a minimum percentage of links bandwidth to each queue. If this bandwidth is 5 mega, it can guarantees for this queue, for let's say for example 2 mega, and this queue 1 mega. If all queues have a large number of packets, each queue gets the percentage bandwidth implied by the configuration. However, if some queues are empty and don't need their bandwidth for a short period, the bandwidth is proportionally allocated across the other queues. What this means? It means if, for example, this queue has no packets for some time, the bandwidth, the allocated bandwidth can be used by this queue for this specific period. So the following table summarizes some of the key features of the class-based weighted fair queuing. As we mentioned, the features for each tool are classification. So class-based weighted fair queuing uses classifiers based on anything that the MQC command can match, like access control list, like network-based application recognition. For drop policy, it uses tail drop or wret configurable per queue. What is tail drop? It is defined here. When a queue is full and iOS has no place to put newly arriving packets, so it discards them. The number of queues, it is 64. The maximum queue length, it depends or varies based on router model and memory. Scheduling inside a single queue. Inside a single queue, it is first in, first out on 63 queue, or weighted fair queuing on the class default queue. Scheduling among all queues. Result of the scheduler provides a percentage of guaranteed bandwidth to each queue. So for the class-based weighted fair queuing configuration, we use the following commands. Actually, you have only 3 or 4 commands, but mainly we use the first and the second. And for the class default, we can use the last one. So what are the commands? It is bandwidth, and you define either the bits or the kilobit per second, the bandwidth kilobit per second as a value, or a percent of the bandwidth of the link bandwidth, and you define the percent. So this class subcommand sets percentage bandwidth for the queue or specific value. The second command, you can define bandwidth and use the remaining percent. What is this? It sets percentage of remaining bandwidth for the queue. What this means, if you assign, for example, 50% of bandwidth to a specific queue, the remaining bandwidth can be configured using this command, the remaining percent. So the third command, queue limit, and you define the queue limit. This class subcommand set the maximum length of a class-based weighted fair queuing queue, the maximum length for that queue. And the last command, fair queue, and you define the queue value. What this means, or it means that this class subcommand enables weighted fair queuing in the class, which is the class default only. So let's give an example for configuring class-based weighted fair queuing on this scenario. We have here a network, a LAN, we call it LAN 1, and we have here something like a WAN, and we have here another LAN, or LAN 2. What are the requirements? The requirement is that we need to configure quality of service queuing using the tool class-based weighted fair queuing for VoIP in one queue and all other traffic in another queue. So we will just make one queue, and as we mentioned, there is a class default queue that matches the packets that does not mention or matches the first command. So the first class. Let's start by configuring class-based weighted fair queuing, and we will use packet tracer. So I prepared that scenario exactly, and we will start by configuring router 3. Let's make it bigger. So we will choose first, or we will classify packets based on access control lists. So let's create an access list, extended access list, 100 permit IP, and we will choose the source any, and the destination host is router 1, because router 1 here acts as the call manager for the voice traffic. So the IP address is 10.1.1.2, and then we will create a class map match all, and we will call it VoIP traffic. And we will call match class group. Let's see here, access group, sorry, to match the access list 100. Now classification is configured. Then let's create a policy map, and let's call it Q-VoIP, and choose class VoIP traffic. And then only one command, bandwidth. Let's give it the VoIP traffic over this link, 10.4.4.0/30, 50% of the bandwidth for voice. So we will give it, if you will look for, you will find out that we have three options: either to configure the number of kilobits per second, or the percentage of the total bandwidth, or the remaining percentage of the remaining bandwidth. But in this scenario, I'm going to give 50%, let's give it percent and 50. Now we created a queue called voice traffic, and inside this queue, all the voice packets will have a bandwidth of 50%. The last thing, we need to configure or associate the configuration to a specific interface. And that interface is, let's see here, serial 1/1. So let's go to this interface to apply the policy map. Interface serial 1/1 using service policy, and as we mentioned, output only, and for this policy map. Let's do some show commands to see the configuration and the traffic that matches the policy map, the access control list, sorry, and whether the quality of service will be applied for this traffic or not. First, we will do show policy map interface serial 1/1. And as you can see here, there are two packets matches, and 50% of the bandwidth is reserved for this traffic. And let's do some calls here. We are calling from LAN 2 to LAN 1, and then we will check the number of matched packets. It became 9. It means all VoIP traffic matches this specific access control list, and it reserves a bandwidth 50% of this serial interface. Let's do another show command, show policy map, to see the configuration. As you can see here, the policy map created a queue for that class VoIP traffic and reserved the bandwidth of 50% of the total bandwidth of the serial link. For now, we finished the discussion or the demonstration of the class-based weighted fair queuing. Then let's go to the second tool, which is called low latency queuing. Let's bring the pen. LLQ looks and acts just like class-based weighted fair queuing. Sorry. In most regards, except it adds the capability for some queues to be configured as low latency queues. What this means? It means if you have a router here with 2 queues, and then you need to give some queuing features for one queue over another to give it low latency. And latency means delay. Using LLQ, you can give some feature for one queue over another. And LLQ schedule these specific queues as strict priority queues. In other words, LLQ always serves packets in these priority queues first. If you give this queue a priority 1 and this queue priority 2, if P1 is bigger than B2, then this queue will exit first, and then this queue will exit second. Sometimes a single low latency queue is called priority queue. So, as a definition for prioritization, giving priority to one queue over another. While LLQ adds a low latency queue to class-based weighted fair queuing, it also prevents the queue starvation that occurs with legacy priority queue. What this means? It means that LLQ actually prevents the queue starvation. Queue starvation means if we have more than let's say four queues, and this queue weighted so much because this one goes second and this one goes third, so this queue will be starved or have starvation because it needs to be processed. So LLQ prevents this queue starvation that occurs with legacy priority queue. LLQ actually policies, and we will know what is the policing in a later video when we just demonstrate shaping and policing. So LLQ actually policies the priority queue based on the configured bandwidths, and policing means that I hope we give a definition here. The bandwidth gives to an LLQ priority queue is both guaranteed minimum and policed maximum. Policing means that we determine a specific level or rate for a specific queue. So in effect, the bandwidth gives to an LLQ priority queue impose the guaranteed minimum and policed maximum. As a result, the packets that make it out of the queue experience low latency, but some might be discarded to prevent starving the other queues. What this means? It means that if we have here a Q1, Q2, some packets from here may be discarded to prevent starving the other queues. Here we will discuss the low latency queuing configuration. It is exactly or almost exactly the same as weighted fair queuing, except instead of bandwidths, we will use priority. So LLQ configuration requires one more command in addition to the commands used for class-based weighted fair queuing configuration. As we mentioned, instead of bandwidths, we will use priority. This class subcommands enables low latency queuing in the class. Reserves bandwidths, so as we mentioned, it works with the class-based weighted fair queuing and enables the policing function. What this means? It means the LLQ reserves bandwidths. If we have two queues here, and you configure priority on this serial interface, the LLQ reserves bandwidths from this link for that queue and enables the policing function. You can also configure the burst size for the policer with this command, but the default setting of 20% of the configured bandwidth is typically a reasonable choice. This default is 20%. So for the same example, we will configure VoIP in one queue and all other traffic in another queue. So let's go to the configuration and just configure low latency queuing. So let's first remove the policy map. And then we will configure the same policy map, but this time with the priority command, and we will see the effect on the traffic. Let's call it QVoip. Class, we defined, I think, VoIP traffic using the same access control list, by the way. And then use the priority command. And look here, you can define either number of bits per second or a percent. Let's give it 50 or 60%. Let's write first percent and then 60%. It gives us here must deconfigure bandwidth before issuing this command in this class. Okay, let's know bandwidth 50 and then repeat the same command. But I think we removed completely the policy map. So we configured priority with percent 60%. Let's go to the show commands and see the effect. Show policy map interface serial 1/1. You will see that the bandwidth taken 60% for that queue, and there are 91 packets matched, and the burst size is defined here, which is 20% by default. All other packets that doesn't match goes to the default class default queue. So the configuration is that simple. Last thing we want to discuss here, how LLQ reserves bandwidth. If the interface bandwidth is 256 kilobit per second, let's say we have a router here, and this link has bandwidth 256 kilobit per second, and you defined 3 queues or 3 classes, class 1, class 2, and class 3. How bandwidth will be assigned to each class based on the priority command. Let's say the first command was priority 32. So let's first say something that 25% in this example is unreservable bandwidth. So if you will calculate 25% of the 256K, the end result will be 64 kilobit per second. This is unreservable bandwidth. So the first priority command reserves 32 kilobit per second. So the remaining is 192 kilobit per second. 192 minus 32 kilobit per second defined for this class, and this for class 2 priority percent is 25. 25 means 64, then minus 64, and the end result will be 96. So this 96 for class 3, the bandwidth command, the priority command uses the remaining percent, but here the bandwidth, not the priority command. So you can apply POS tools in the same, we're applying here POS tools in the same example, but with remaining percent 75, and 75 of the remaining 96 equals 72. This is how the total bandwidth is reserved for 3 different classes. 25 is unreservable bandwidth, 32 bits for class 1, 64 or 25% for class 2, and remaining percent 75 of the remaining equals 72 for class 3. Then we have remaining bandwidths of 24 kilobit per second unallocated. So let's see how LLQ with more than one priority queue. LLQ allows multiple queues to be configured as priority queues, because you can have, let's say for example, 3 queues. Only 2 are configured as priority queue, and each queue has a specific configuration. One will be preferred over another, or one will have specific reserved bandwidths, and so on. So when you have multiple queues configured as priority queue, this begs the question, which queue gets scheduled first? Because both are priority queue. As it turns out, low latency queuing actually places the packets from multiple LLQs into a single internal LLQ. What this means? It means that the low latency queuing places the packets here in a single internal LLQ. So packets in the different configured priority queues still get scheduled ahead of non-priority queues, but they are services based on the arrival time for all packets in any of the priority queues. So why use multiple priority queues? The answer is policing, and in more details we will discuss policing in another video. By policing traffic in one class at one speed, and traffic is another class at another speed. What this means, if we have here 2 queues, one will be policed for a specific speed and the other will be policed for another speed. And for example, if you are planning for voice and video, here will be clear for this example. You can place each one into a separate LLQ, get low latency and get low latency performance for both types of traffic, but at the same time prevent video traffic from consuming the bandwidth engineered for voice and vice versa. Let's say we have 2 queues. some packets here for voice, and some packet here for data. To prevent one class of packets to starve the other packets, we can do policing. So the LLQ do an internal queue, single internal queue for each one, and do some policing for each queue and prevent the one traffic to consume the bandwidths over the other. So finally, iOS uses queuing only when congestion occurs. If there is no congestion, the iOS queuing tool will not have any benefit because it can be used only when congestion occurs. Because if there is no congestion, the packets will be serviced without latency, without dropping, and so on. So iOS consider congestion to be occurring when the hardware queue is full, not the software queue. And that generally happens when the offered load of traffic is far less than the clock rate of the link. As we mentioned before, this link was 100 mega, and this link was 1.544 mega. So this congestion happens when the offered load is far less than the clock rate of the link. So a router could have a service policy output command on an interface with LLQ configured, but the LLQ logic would be used only when the hardware queue is full. So till here, we come to end to this video. I hope it's been informative for you, and thanks for watching.